My name is Robert Kay. I'm from the University of Leeds, and I just want to talk to you a little bit about the design challenges and also the opportunities for 3D printed electronic systems. So just very quickly a little bit about myself. I need to use a disclaimer that I'm not a design engineer, so I work on manufacturing processes research. And my research is very much focused on developing digitally driven techniques such as additive manufacturing to produce functional products such as medical devices, wearable systems, and robotics. So all of these are underpinned by electronic systems. One thing that I think is quite unique about the work that we do within my group at Leeds is that we specialize in building new machinery. So it means that we don't go out and buy an additive manufacturing machine, but we actually build the systems up from the ground. And I think that allows you to develop a lot more in terms of a new process, but also to be able to develop new IP. And this is all framed within 140 meters lab that we have all this dedicated skills to build these machines. Before we start, because it's very much a topic on design for additive manufacturing, I thought I'd better just very quickly explain what an electronic system is. Now, I don't need to tell you the impact of electronics because they're ubiquitous in modern society. You know, we're doing this call via Teams, so all of you are on some sort of electronic system to access this call. But when you look at an electronic system, it's quite a complicated beast. It's made up of a mixture of different components. So typically you have something like a printed circuit board, which provides the route for all the components to communicate. So that's almost like a network of roads, which allow these different components to communicate with each other. On top of this PCB, you would normally have integrated circuits, such as microchips, which are packaged on top of that board. And that acts like the brains of the system. So things like microprocessors and memory. On top of that, you'd have discrete devices connected to the PCB, so things like resistors, capacitors, and diodes. And then finally, in modern devices like a smartphone, you normally have additional things like sensors and actuators. So they might be the camera module or the accelerometer that notes that it's able to sense when your phone's tilted, or the antenna that gives you your Bluetooth or your 4G communication. So really these act like the eyes, the voice, the ears of the system. And I've highlighted in green areas really where 3D printing can make an impact, where you might want to fabricate these parts. And realistically, a lot of the other components, like the microchips or the discrete components, albeit you might be able to look at printing those, realistically, the way that they're manufactured and the sizes of those, you want to incorporate them within the 3D printed structure. Now, if we think about the drivers in electronic design, I think they're a little bit different to a lot of the drivers and the motivation in additive manufacturing. So the first driver really is that we want the highest performance systems, and that they're portable, they're lightweight. So you're trying to design the most compact system. But furthermore, you want the battery life on your mobile phone to last more than a few hours. So you're trying to design efficient systems that reduce power consumption. This problem's, I guess, compounded because when you reduce the size of components and you shrink this density, you have more heat dissipation. So you need to design for thermal management. Not only that, when you look at the image on the slide here, you can see that these are very complicated systems. They're multi-layer boards. There's routings going between many components. Some of the components have many input outputs. So you don't want to manually be drawing those traces, so you need some form of design automation. Also, you know, since the 60s or the 70s, there's been this rapid evolution of the complexity of electronic systems, and they're now that complicated that really you need very good design analysis and practice. Finally, consumer electronic devices have a very short lifespan, and there's a requirement to get these to market very quickly. So design reuse is becoming more important as a driver in electronic design. Now, when we think about the motivations around 3D printed electronics, these are a little bit different than perhaps the motivators around electronic systems, but you can see some real benefits of potentially adopting digitally driven approaches like 3D printing. The first thing, obviously, is mass customization and also for product development. Also, because it's not a template-driven process, you have the potential for producing very high-value products at low volumes. In theory, you can increase complexity. I wouldn't really say complexity in the density with the current technologies, but more the geometric complexity. You can also consider to add functionality within the part rather than having to add that in separately. So maybe integrating cooling channels or electromagnetic interference shielding, or even when you look at autonomous systems, actually incorporating actuation and movement into the parts. Another motivation would be that if you look at traditional electronic systems, you normally have a board, maybe a rigid PCB or a flex substrate, and then that's incorporated into a package housing. Where with 3D printing, you can start to make the package housing part of that substrate. So you're combining the two together. And overall, I think the major driver is that it aligns to the sort of factories of the future, the digital manufacturing vision, where you can incorporate 3D CAD design, modeling and simulation, increased robotic assembly, and all these things, the benefits that you get with a sort of Industry 4.0 vision. However, there's a lot of challenges and potential opportunities that remain. So the rest of my presentation, I'm just going to focus on a few examples that primarily focus around my research, but it shows you some of the limitations I have when I'm trying to design an electronic system. So one of the first limitations with 3D printing, additive manufacturing, it's been around for a while, more than 30 years, and there's a range of different processes, and they can do polymers, metals, and ceramics. But none of these processes really can do the multi-materials of joining different material classes very effectively. So what you're finding is the majority of the research looks at combining different 3D printing processes or 3D printing processes with other digital techniques such as direct write processing, such as aerosol jetting or dispensing or material jetting. So that creates a lot of limitations on the design when you're interleaving these different techniques in quite an ad hoc process. This example here that I'm showing you, this is a very basic 555 timer circuit that we produced a few years ago. And albeit we're able to use modern components, there's only about 10 components here. And realistically, our design was very limited. Because we wanted to get multi-layer to get the density up there, we had to even print the Z-axis interconnections. Normally in a PCB, these would be vias. But even to generate these out of a conductive paste was a bit of a challenge, just figuring out how you design those pillars so they don't slump or fall over. And also, once you produce the part, say, in this case, we produced the dielectric medium, the substrate, out of stereolithography technique. We then have to take that out the stereolithography bath. We need to clean that down. We then need to align it so that we can then dispense the conductive medium. We cure that conductor. Then we put additional interconnect material and the components, and we cure that. Then we have to put it back into the stereolithography bath and align that. And so what would be quite an automated 3D printing process becomes a very ad hoc manual technique. And that really does limit some of the design freedoms, especially when you look at the components here that are flat. So you're still almost aligning to a 2.5D vision rather than a 3D vision. It's not just the multi-material challenge that gives limitations for electronics. If you look at pastes and inks, which are commonly like inkjet printed or dispensed, they really have resolution issues, lateral resolution issues when you compared to standard PCB manufacture that would use techniques like photolithography and etching or electroplating. Also, these materials that you're designed for printing, they're typically pastes or inks that have been loaded with metallic particles. So you never get the same conductivity as PCB circuitry, which normally made out of the bulk copper itself. So suddenly you've got these resolution images and issues, I should say, and these performance issues, which means that really 3D printed electronics are like going back to the 1970s in many ways. So you're having to you're not able to use maybe the most modern components. You're not able to get that density in the circuitry, and therefore you're not able to design in the functionality that you would like. So this next example I wanted to show you from my research is basically trying to overcome some of these issues to open up the ability to design complex systems. And the first thing we realized is that most 3D printed polymers are quite low temperature, and they don't necessarily have the dielectric properties suitable for electronic systems. So we were able to print polyetherimide using a standard fused filament fabrication process, but just increasing the temperature of the build system. What's quite nice about this material is that it's very chemically inert. It's got high temperature properties, but it's also got excellent dielectric properties. Furthermore, it's got a functional imide group, which means that if we put it in a very caustic solution, we can crack that imide ring, and then we can embed in metallic ions. In this case, we've embedded silver ions. If we then shine a laser onto the chemically treated 3D printed substrate, we're able to selectively reduce nanoparticles, silver nanoparticles. And these nanoparticles then act as a seed site for electroless copper plating. So suddenly we've got the lateral resolution of a light-based patterning process for making the conductors. We've got a high temperature substrate with great mechanical and dielectric properties, but also we're able to put down the copper just like PCBs, so you get that bulk conductivity. And then we combine this with robotic dispensing and pick and place to align to that fully digitally driven vision. And here's an image of that demonstrator, that visual demonstrator. And even though this looks quite fancy, it's a pretty demonstrator, we still had design challenges here. You know, where we put that component, we had to take that bio-inspired butterfly shape and we had to flatten its back so we could put a flat component on it. Where we put the antenna circuitry on the abdomen of the butterfly, we were using a Formlabs stereolithography printer, so we hacked it, and that's really an XY system. So we had the image projecting over the 3D profile. So we had challenges about how you design that and link that with a toolpath. We were taking a planar image and putting that onto a 3D surface. However, I think this is very exciting, and I need to really acknowledge the excellent collaborative effort from Harriet Watt, who were able to demonstrate the underpinning material science here. But also thanks to EPSRC who funded this work, because it's quite speculative and difficult to get funding, that they were willing to look at these new concepts that could have a transformative impact in our field. And taking this particular process forward, I want to start off with something that's quite obvious. You would think that if you're able to 3D print electronic systems, that you'd be able to get, if you move from a planar to a three-dimensional shape, you can get this in a much more compact format. So here we've taken a standard antenna design, which the substrate's over 40 millimeters in diameter, and we've wrapped that around a pill capsule that's 13 millimeters in diameter. So the aim is eventually to have ingestible 3D printed medical devices, for example. And this all sounds great, it sounds wonderful, but when we actually tried to do the design, the simulation, and the manufacturing, it was very ad hoc. Let's try it out. Let's see how the simulations align to what actually came out from manufacturing. We weren't able to simulate the impact of layering or any of these things on the properties. And another big thing is that with the 3D printing on a design limitation is it's not just the conductor properties or the resolution, but it's also the dielectric medium, the polymer that's important. And a lot of times the materials have been designed for printing, but not for wireless communications or RF applications. Another thing I wanted to get people to think about today is, how do you design electronic systems for reliability? How do you design bespoke products that still pass consumer requirements? Now, if you take a modern mobile phone and you drop it from about waist height, you might crack the screen, but the electronics within it stay together, they still perform. And that's quite important. That's a reliable and robust system. That system could easily go up to a fairly high temperature and even be put in a freezer, and these components still wouldn't be broken, it wouldn't damage. Well, when you look at 3D printing, you're depositing maybe through inkjet printing or aerosol jetting or dispensing onto a dielectric medium. And so you have issues with the adhesion of the conductor layer, that reliability. Typically also, when you think about 3D printing, you're using low temperature polymers. So you can't even use standard surface mount packaging processes that use solder, which give these electronic products that great degree of reliability. Mechanical performance too. You've got a layer by layer process, so you're not getting the same performance as the package housing on, say, a injection molded component. And finally, and this is quite an important one, if you take mass-produced electronic consumer goods, the production process has been refined and refined, so the yields there, but also the reliability, because they're able to do like destructive testing or long-term reliability testing. For example, sticking these into a thermal cycling oven and accelerate age testing them. How do you design this with 3D printing when you're looking to make low volumes or one-off parts, and you've got all these other trade-offs with the materials and the resolution? I'm not saying I've got a solution for this, but I wanted to show an example based on that process that we've been developing. Because we're printing a much higher temperature thermoplastic and we're able to put down bulk copper, you've suddenly got a wettable surface for putting solder down onto. And the great thing about solder is that you can get a metallurgical bond between the substrate and the component. So that gives you a very high reliability. So what we're starting to demonstrate is that we can package modern components such as microprocessors and memory, and also really small discrete components going all the way down to just over the size of a grain of sand. And when you can start to take these different components, it allows you to be able to design very complex 3D printed electronics. So it's starting to go in the right direction here. Another big advantage of 3D printing I think for electronics might be reducing assembly. It allows you to consider how you might incorporate more of the mechanical and the electrical system into one single component, one single product. So this is particularly important when you think about, say, robotic and autonomous systems where they have both movement and the electronics in there. But I have to ask that question and ask, especially the designers, is reducing assembly always the best route forward? If you look at mass-produced electronic systems, they're able to use these different components that are mass-produced, but choose their configuration, their architecture to give different functionality. So they actually get modularity freedom in the design. But not only that, it reduces manufacturing costs if you can get mass-produced components and then put them into your system. Also, for example, if somebody makes a camera module for your mobile phone, somebody makes a logic board for it, and somebody else does the assembly of these components, and then maybe somebody else does your battery, you can bring all these individual components together and in a way control your reliability. Where if you try to print all of these in one go, if you have any yield issues on that area because you've got so much complexity, you've lost a whole part, you've lost a whole product. So that sometimes reducing assembly might not be the best route forward in design. However, I think there is some opportunities here, and I want to get people thinking about that. If you look at like your laptop, for example, typically it's hinged. So you've got like your motherboard, your logic board, and then you'd have your display. And in order to get that display to be able to hinge and close the roof of the laptop, you've normally got some sort of flexible PCB that connects the rigid boards. And those connectors are quite bulky, and they're often a weak spot in the design. So what's quite nice about the particular process I'm showing you here, this combined 3D printing technique, is that we can print very thin regions of just a couple layers, and we can print thick regions that become stiff. So we have flexible and rigid in the same area. And actually, if you think about it as a designer, you can actually print a variety of different layer thicknesses. So you could even start to consider tunable stiffness of the parts by printing in this way. And taking that a step further, if you think about it, maybe in the future, you'd want devices that you could maybe post flat pack through your mailbox, and then they would open up. So if you can start to incorporate actuation within the 3D printed structures, this is going to give you new degrees of freedom. And in this case here, I'm just showing you something where we've incorporated shape memory alloy into the individual printed circuits that we use as heating elements, and we can selectively actuate these now. And if you think about it, it's really exciting. You could have 3D printed electronics that are origami electronics or maybe bio-inspired designs. And I'm just conscious of time here, so I'm just going to very quickly give one last example. A great benefit of 3D printing, really, I think, is the spatial control of materials. So normally when you see in designs of, say, antennas, like in this case, a Bluetooth module, normally you're fixed with a rigid dielectric medium and you can change the shape of that antenna. But actually, if you're able to dynamically alter the effective permittivity, and this is some work that I actually did with Loughborough University a few years ago, where we used a standard stereolithography process and we changed the volume of air inclusions, we're able to change the permittivity of that substrate. And that opens up completely new design opportunities for RF and antenna designers and maybe people thinking of making meta devices in the future. So just to conclude, I'm sorry, I think I'm about a minute over here. I think there's tremendous potential for the design of 3D printed electronic systems, but there's still a lot of challenges about how you link the design, simulation, and manufacturing together. But you've got all these great opportunities around making more complex, lightweight products, that spatial control of materials, greater integration of the electrical and mechanical systems, and finally, bio-inspired and origami designs. So thank you very much, everybody.